Hello everyone, this is Madhuri working as an assistant professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology. Today we are going to discuss about transformer. In transformer, we are going to discuss about the topic of EMF equation of the transformer. So we can see that in a transformer, we have a magnetic core and the windings as the essential parts in the transformer. So in windings, we have primary winding and secondary winding. So in magnetic core is a common path between the two windings, that is primary winding and secondary winding. We have seen that a supply is connected to the primary circuit or primary winding of the transformer, and we have seen that a load is connected to the secondary winding of the transformer. So when supply is given to the primary winding of the transformer, an alternating flux is set up in the magnetic core. So this alternating flux, according to Faraday's laws of electromagnetic induction, so the flux linkages in the magnetic core or the windings to which the supply is given, there will be an EMF induced in that particular winding. So when we give supply to the primary winding of the transformer, we can see there is a magnetic flux, alternating magnetic flux set up in the primary winding of the transformer, which in turn induces EMF E1, which is responsible for the flow of current I1 in the primary circuit of the transformer. So this induced EMF in the primary winding of the transformer is due to Faraday's laws of electromagnetic induction. So this EMF E1 is responsible for the flow of current I1 in the primary circuit of the transformer. So this alternating flux, which is responsible for the production of EMF E1 in the primary circuit of the transformer, will link to the secondary winding of the transformer, where it produces the induced EMF E2 with the process of mutual induction between the two coils, that is the primary winding and the secondary winding. So due to mutual induction between the primary winding and secondary winding of the transformer, an EMF E2 is induced in the secondary winding of the transformer, which is responsible for the flow of current I2 in the load of the transformer. So basically we can see that supply is connected to the primary winding of the transformer and the load is connected to the secondary winding of the transformer. So this entire Faraday's laws of electromagnetic induction and the mutual induction process, which is happening in the working of transformer, will set up an alternating flux phi. So this alternating flux phi is also in sinusoidal nature. So we can see the waveform of the flux phi here in the sinusoidal form. So we can see that the entire time period required for the one complete cycle of the flux, alternating flux in the primary winding of the transformer, is nothing but the time period t. So if we give the time period t in terms of frequency, it is given as 1 by f. So the time taken for completion of one complete cycle of the alternating flux in the primary winding of the transformer is nothing but called as time period. So if it is written in terms of frequency, it is written as a reciprocal of frequency. So this flux phi, it has a positive cycle and negative cycle. The time taken to complete the positive cycle of the flux is nothing but half of the time period. So it is nothing but 1 by 2f. So the time taken in terms of frequency to attain the maximum peak value of the flux in this entire cycle of the flux, alternating flux cycle, is nothing but half of the positive peak. So here the time taken for the flux to attain the maximum value is given as 1 by 4f. So this particular instant of time period for which the alternating flux to reach its peak value is nothing but given as T is equals to 1 by 4f. So when there is a sinusoidal voltage applied to the primary winding of the transformer, a flux is set up in the transformer. So maximum flux sets up in the iron core of the transformer. So this, as the core is the common path for the flow of flux between the primary and secondary windings of the transformer. So this sinusoidal flux links both primary and secondary winding. So we have seen the sinusoidal function of the alternating flux, and the time taken for the flux to attain its peak value is nothing but T is equals to 1 by 4F. So the rate of change of flux with respect to time, if we derive it mathematically with respect to Faraday's laws of electromagnetic induction, we get the EMF equation of the transformer. So let us consider phi m be the maximum value of flux, which is shown in this alternating cycle of the flux. This phi m is the maximum value of flux. F is the supply frequency of the AC supply given to the primary winding of the transformer. It is basically 50 Hz. N1 be the number of turns in the primary winding and N2 be the number of turns in the secondary winding. And let us consider flux. Phi is the flux per turn in Weber. As we have N1 and N2 turns in the primary and secondary winding of the transformer, let us consider the flux per one turn is nothing but, let us consider it as phi. So as shown in figure, we have seen that flux changes from positive phi m to negative phi m. So it reaches maximum peak values in both the positive cycle and the negative cycle. So its range of the flux ranges from positive phi m, the peak value of the flux ranges from positive phi m to negative phi m in a half cycle, that is nothing but 1 by 2f of the supply frequency. So let us consider E1 be the induced EMF in the primary winding. According to the Faraday's laws of electromagnetic induction, we can say that EMF induced is directly proportional to the rate of change of flux linkages in any conducting coil. So this negative sign is due to the Lenz's law, which is happening between the main flux mutually induced EMF E1 and the self-induced EMF in the primary winding in respective windings. So according to Faraday's laws of electromagnetic induction, an EMF is induced in a current carrying conducting coil when there is a change in flux with respect to time. So this negative sign in this expression is due to Lenz's law. This Lenz's law is between the mutually induced EMF and the self-induced EMFs in both primary and secondary windings. Let us consider the flux linkage in the primary winding as the number of turns in the primary windings multiplied by the flux in each turn. So this will be the total flux linkages in the primary winding. And let us consider the instantaneous value of the flux as phi is equals to phi m sin omega t. So when you substitute the value of phi and this flux linkages in the equation 1, here phi as flux psi as N1 into phi and phi as phi m sin omega t. So upon substituting these two values in equation 1, we get the relation as minus N1 into omega phi m cos omega t. So we have a negative sign here, we have the cos term here. We can rewrite this minus cos omega t in terms of sin omega t minus 90. So the entire EMF equation is now reduced to, in terms of number of turns in the primary winding, it is nothing but omega, the angular frequency. It is nothing but the phi m, the maximum peak value of the flux, alternating flux, and the sinusoidal component of the flux. So from this relation, we can see that induced EMF E1 is lagging the flux phi by an angle of 90 degrees. So we can say E lags phi by an angle of 90 degrees from equation 3. So from this previous equation, we can take this value of the flux as maximum value. So I can rewrite this equation as Em sine omega t minus phi by 2. So from this relation, we can say that E maximum is equals to N1 omega phi m, which can be seen in equation 4. So upon substituting omega as 2 pi f, as we know omega is equals to 2 pi f, substituting the value of omega here, we get the maximum value of EMF induced in the primary winding as 2 pi f into number of turns in the primary winding and the peak value of flux in the alternating cycle of the flux. From this, the root mean square value of the flux. So we can RMS value of induced EMF E1 is nothing but maximum value by root 2. So maximum value, we have got it as 2 pi f n1 into phi m. So upon dividing it by root 2, we get the respective equation of EMF induced in the primary winding as root 2 into pi into f into n1 into phi m. So upon substituting the pi value as 3.14, we get the relation for induced EMF E1 in the transformer primary winding as 4.44 f into n1 into phi m. Similarly, we get the relation for the induced EMF in the secondary winding of the transformer as, similarly, upon solving all the above steps for the flux linkages in the secondary winding as shown in the equation 1, if we substitute it for the secondary winding, we get psi as n2 into phi, and the instantaneous value of flux remains the same, that is nothing but phi is equals to phi m sine omega t. Upon substituting all these values and deriving all these steps again for the induced EMF E2, we get the induced EMF E2 as 4.44 into f into n2 and phi m. So we have equation 8 and equation 9. So now upon equating the equation 8 and 9, we get the relations as E2 by E1 is equals to N2 by N1, which is again equals to K. So K here is nothing but the transformation ratio. So if we consider phi in terms of B and A. So what is B? B is basically the flux density, magnetic flux density. So the relation for flux in terms of magnetic flux density and area of cross section is nothing but phi is equals to B into A. So when we further write these equations EMF E2 and E1 in terms of B and A, we get the relations as E1 is equals to 4.44 into N1 into F into Bm. Bm is nothing but the maximum flux density in the primary winding of the transformer, and AI is nothing but the area of cross section. That is nothing but the area of cross section up to which the primary winding is wounded on the magnetic core. So this is nothing but AI. So for the secondary winding of the transformer, we get the similar equations in terms of N2. So number of turns as they vary in both the windings. So for the primary induced EMF, we take E1 as N1, and for E2, we take it as N2. So if we consider a lossless transformer, or transformer in an ideal case. Ideal case means the transformer upon no load. So when the transformer is not loaded, the input power will be equals to output power. So input power, we have seen the supply, AC supply as V1 into I1, and the terminal voltage across the load as V2 into the current in the secondary winding as I2. So from this relation, we get the equation for V1 by V2 as I2 by I1. So this is the relation for the supply voltage to the terminal voltage and the respective currents in the secondary winding and the primary winding of the transformer. So when we overall write all these equations together, consider this as equation number 10 and consider this as equation number 11. So when we consider these equations, we can rewrite the entire EMF equation of the transformer and the transformation ratio in terms of induced EMFs, which is again equals to N2 by N1, which is equals to K. So this entire relation between the induced EMFs and the supply voltage and the terminal voltage and the primary current and the secondary current and also the number of turns in the primary winding and the secondary winding is equated to a term called K, transformation ratio, which plays an important role in deciding the rating of the transformer. So this is about the topic of EMF equation of the transformer. So while discussing about the EMF equation of the transformer, we have seen that flux phi is also in alternating nature, which is in alternating nature is responsible for the prediction of EMFs E1 and E2 in the primary and secondary windings of the transformer. So considering the instantaneous value of the flux, phi is equals to phi m sin omega t, and also the Faraday's laws, we have derived the equations for E1 as into N1 for the primary winding of the transformer and EMF equation E2 as for the secondary winding of the transformer. This is about the EMF equation of the transformer, which is basically used to decide the rating of the transformer and also to calculate the transformation ratio K with respect to the terms V1, V2, I1, I2 and also N1, N2. Thank you.